switches get root canals. Take it away.
All right. So I will jump in. Let me get this going. This on. So this is originally this talk was called Network Switch Inception. So it's a look at network switches to see what cool stuff we can do with network switches once we compromise them. So this is not a talk about vulnerabilities. It's kind of inspired by a bunch of talks about network switch vulnerabilities. There was a series of talks called Switches Get Stitches a couple of years ago that happened at Black Hat and DEF CON and a couple of ICS security conferences. They found a whole bunch of different vulnerabilities in network switches, specifically in the industrial space. There have been a lot of other, vulnerabilities and backdoors in Cisco and Juniper equipment lately. There was the Sophos one that was exploited in the wild last month. And 2 years ago, there was this big ICS, or actually, I guess this was a DHS advisory or alert that came out saying that a lot of network equipment was being targeted by bad guys trying to get into different networks. So this is not a talk about those vulnerabilities, though. This is a talk about post-exploitation, right? In other words, let's say we have a typical layer 2 managed network switch that's got like very little in terms of capabilities. It's really just meant to do packet matching from port A to port B and deliver packets from one port to the other. Might have a few neat features. Usually these things have network port mirroring, as well as VLAN tagging and all that sort of stuff. But this is really a question of like, let's say we find a vulnerability in a network switch. What can we actually do with it that's useful to an attacker from that point on the network? So the victim that we're going to look at for this talk is this industrial Ethernet switch called the 6net EtherTrack ET9MS. It's a 9-port 10100 managed network switch. It's a couple of years old, but although 10100 switches sound slow in the industrial space, you don't find too much gigabit Ethernet still, because most of these like industrial controllers don't even have gigabit Ethernet in them. So people use these old, tried and true, slower network switches. I chose this switch mostly because it has this little penguin logo on the front, which suggests that it runs embedded Linux under the hood, which turns out to be true. So we popped open the switch just to kind of get a feel for what we were working with in terms of hardware and software. This thing has a little Atmega or Atmel, ARM9 CPU. That thing runs at 200 megahertz. It's got 128 megabits of flash to hold the flash file system for the embedded Linux. And it has this Marvell 88E6083 switch chip. It's also known as the Easy Street switch chip. So again, this is a 9-port Ethernet switch. It's meant to have 8 normal ports that you plug field equipment into, and then 1 uplink port that would be connected upstream to, probably some upstream data center or something. So the actual vulnerability that we use to get into the switch is nothing super special. And I said this wouldn't be a talk about vulnerabilities, but I'll at least touch on it. It's a directory traversal bug. If you back up the configuration of the switch and look at it, it's actually a tarball. You can see, it's backing up a bunch of different directories on the switch. We were able to use another little directory traversal bug to read some of the configuration files and then upload a backed up configuration that happened to have a new Etsy password and Etsy shadow file in it. So then we could, also enable the embedded SSH server, log into the switch and have a root shell. We did report it to the vendor. They really didn't care. They were like, well, the switch is end of life, so we're not going to patch it. But this is a talk about post-exploitation, right? So let's say that we've got admin access on this switch, or it could be anything, really. It could be a VPN gateway, whatever. But the question is, now what? What's an attacker going to do with that vulnerability once they actually use it and get access to the network hardware? There's a bunch of boring attacks you can do on a network switch. There's like you could disable network interfaces, you could disable the mirror port, you could probably lock the administrators out. I view those as all pretty boring because that's probably going to be something that gets observed. It would be a lot more interesting to do some attacks that are a little bit more nefarious, a little bit trickier to detect, and then maybe have some more interesting outcomes and impacts against the people who happen to legitimately own the equipment. But the official story is, this layer 2 network switch is really it's just a packet matching engine, right? It says like, okay, I have this MAC address table. I know that MAC address foo is on port 1. I know MAC address bar is on port 2. When a packet comes in and it's supposed to go to, MAC address bar, I send it out port 2 and vice versa. So it's really just supposed to be doing this, addressing based on MAC address. But that's actually not really all that true if we look a little bit more deeply at network switches. So we need to look a little more deeply at this actual Easy Street chip. So the kind of official story is that it's just a packet matching engine, but these things are really configurable. In fact, most network switches, if you can find the data sheets for them, you'll find out that they're not just meant to be used in a switch. They're usually meant to be used in a variety of equipment. Like the same switch chip can be used in switches and routers, and they have a lot of provisions for routing packets to an internal CPU. And we'll look at some of that in this talk. But really, the key thing here is that I wanted to avoid like chipisms. So I wanted to avoid any techniques that were specific to one type of Ethernet switch chip. And I wanted to look at more generic techniques for manipulating packets. And it turns out that those two interesting features, VLAN tagging and port mirroring, can be pretty harmful when put in the wrong hands. Switch chips, as a little background, are configured via this protocol called MDIO. I think it stands for multi-data in-out. I have to look at the Wikipedia page again. I don't even remember. But it's best to think of it as a little serial protocol that lets you read and write the configuration registers of the switch fabric. In the case of the 6net ET9MS, there's not a whole lot to it, but we'll look at it anyway. The operating system, it turns out, can do a lot of the gory details for us. So this is the Marvel Easy Street switch fabric that lives inside of this ET9MS Ethernet switch. And remember, this is an ET9MS, right? It's got 9 network ports. But kind of a pop quiz, how many ports are actually on the switch chip that's inside of it? And if you count, they start at 0 and end at 9, and there are actually 10 ports. That's kind of interesting, right? You're thinking to yourself, like, why are there 10 ports on this 9-port Ethernet switch? And this is kind of a dirty secret of all managed network switches, right? If they have a management service, like a web service or an SSH or Telnet service that lets you manage the Ethernet switch, there's kind of an invisible switch port inside, and that's connected to the little microcontroller. In this case, this is that ARM9 CPU that runs at 200 megahertz. Then usually switch makers, the switch fabric makers, will leave a couple of their ports not connected to any file, and the reason would give you those, what are they called, GBIC. You can plug in maybe like a fiber connector for an uplink, as well as so it turns all of these layer 2 switches that actually become routers and even packet filters, and we'll look exactly at how that works. So the steps to actually turn a regular old network switch into a packet filter are learning what switch port matches to that internal CPU, MDIO commands to reconfigure the switch fabric, and then you have to come up with some neat attacks to change the configuration. And we still don't really know how to profit off of this, but that's okay. So step 1, this is the figuring out what ports match to the internal CPU. There's a couple of ways to go about this. One is if you've got the hardware on your desk, you could take it apart and start tracing out leads and seeing what's connected to what. This switch, turns out there was a nice way to cheat. In the etc directory on the switch firmware, there is this little swm.config file that actually maps out the case port to internal port on the switch fabric. And in this case, the case port 0, which is the case port that does not exist, connects up to port 9 on the switch fabric. And so we knew it would probably be port 8 or 9. If we go back to this data sheet, port 8 and port 9 are the two that don't have a PHY attached to the switch. So it would probably be one of those two, and it turns out to be port 9. So next up, we need to kind of figure out how to manipulate the switch configuration. So this is a couple of different steps. The easy part, quote unquote, was to start looking around the actual switch firmware and seeing how the web interface did it. And the web interface does the switch chip configuration using this library file called libswm.so. And this is the library, because we saw that swm.config being the thing that defines what port connects up to what switch channel. This libswm.so turns out to be the library responsible for issuing commands to the switch fabric. And then once we, kind of have that libswm.so shared library figured out, we'll have to start compiling our own code. Of course, we're going to need to generate a little header file for that libswm in order to write some of our own code, and use a compatible cross compiler to do it. So let's take a look at what's all involved in this. Well, we start loading this libswm.so file. We put it into our favorite disassembler, and we find that, hey, there's a bunch of, this thing is actually compiled with debug symbols. First off, all the exports, of course, are named. There's a lot of useful functions. One of the useful functions is this function called register dump. And register dump, when we start looking through it, looks like it reads out all of the configuration registers from the switch fabric and prints them out to standard out. So that's cool. Now we need to figure out how to actually use this register dump thing. So we can see that it takes an argument on register R0 and then starts treating it as a data structure that it passes to the jmdio read function down at the bottom of this block of assembly code. So we know that it takes one argument, this register dump function. Apparently it's some kind of big data structure. If we start really looking through the code, it looks kind of like this data structure that's published in the Linux kernel source called an MII bus struct, which is usually used for configuring Ethernet PHYs, but some fields in it don't quite line up. So we just start, go back to looking at the shared library and saying, what other interesting functions are there here? Well, there turns out to be a function called find SWM that takes no arguments and returns a pointer to a weird data structure that looks also a lot like an MII bus struct. So maybe we just call this function and see if it works. So we write our own little C file that calls voids out find SWM, so it returns a void pointer. We call find SWM and assign it to our void pointer thing, and then we call register dump with the parameter thing and see what happens. And it turns out that we get the output that's valid. So we get the tool that outputs our global registers. When we start looking through the Marvel Easy Street datasheet, we find out that all of these register configurations match up to what we expect. They match up to, oh, okay, this thing is the target mirror port. This port is the target mirror port. This port is the source mirror port. All these bits work. If I change the configuration using the web application and then run this register dump tool again, we get the information we expect from the switch's configuration registers. So awesome. So we've solved our first challenge. So that's kind of enough with the reverse engineering of the actual MDIO protocol. Actually, there are two functions that are most important in this libswm. Those are the MDIO read and MDIO write functions. They take the weird MII bus looking struct thing as a parameter, and then they also take a register number and a new value to set in the case of read, and they also take the actual channel number parameter. So that's like which port or is it that we're reconfiguring. So we need to make our own little header file that has these entries in the header file so that we can actually use MDIO read and MDIO write, and that's cool. And then we start looking through the data sheets and seeing, okay, what exactly can we configure? Here's the ingress monitor bit. If you set this bit, then the monitor or mirror mode is going to be looking to this particular port and giving its output to the destination mirror port. So we just need to start figuring out how some of this stuff works and how we're going to use those register write functions specifically to overwrite the values here. So we built our own little application to use the library. You can grab the source code if you want to play along at home someday. It's on GitHub under readme first /6net9ms. And the cross build environment, which I didn't talk about, is it's pretty easy to figure out, because if you start looking through all the shared libraries on the ET9 them as their cross build environment, and you can go to the ELDK. They're a German based company that made a whole bunch of cross compiler environments for Linux. You can actually go the things work beautiful. Really, what I would have been doing, like you want to play around with a network switch, wanted to accomplish. And every time defenders are like, oh, I could write an IDS rule to detect your attack, I always want to like one up them or whatever. So the first goal that I really had was like, hey, could I do something where I could manipulate mirror port traffic? In other words, make a fake mirror, basically, where it mirrors most of the traffic to the mirror port. So your IDS sees what looks like normal network traffic, but then hide stuff. Like, hey, maybe there's a particular, source MAC address that I don't want the IDS to see, something special. And then the other question that I had was, can we do any kind of like advanced packet filtering? Like, hey, can we take a network switch and either modify data between two hosts, or just drop data between two hosts? And like I said earlier, we kind of want to avoid chipisms. So this particular Easy Street chip, it's really meant to be used in either a network switch or a router. So it has a lot of features that let you say, okay, these two ports can talk to each other, but they actually have to route through the CPU in order to do that. We wanted to avoid doing that. We wanted to look at more generic attacks that could be used against an Ethernet switch that maybe had a less capable switch fabric inside. So normal port mirroring, this is kind of what you do. And again, I'm an industrial guy, so I have kind of an industrial focus. Like normally you would have, let's say a host connected to one port and an upstream LAN connected to another port. And you would probably want to like mirror all the traffic to and from that upstream port, since that's going to probably represent, at least the initial phases of an attack on your network. And you want to put those over to a dedicated mirror port that your IDS is then hooked up to and monitoring. So that's how normally how mirror ports work. But in this case, we're naming this attack the Leverett attack after one of the Switches Get Stitches crew, Aaron Leverett. He's a really cool guy. We want to first find the port that the user is mirroring to. We do that using those, those Reid MDIO commands to the switch chip, and then doing some comparisons of bits. Then we want to reconfigure the switch chip to redirect that port mirror. And instead of directing it to the outside facing port, we're going to redirect the port mirror to the microcontroller that sits inside of the switch itself. And then using the chip or the processor that's on the switch itself, we'll sniff the traffic. We'll decide if the incoming packet is one that should actually be seen by the IDS or not. And if it's supposed to be seen by the IDS, meaning it's a benign packet, we'll just temporarily enable another mirror port, but this time we'll define the internal microcontroller's port on the switch fabric to be the source port. We'll send the packet, then we'll disable the mirror port on the microcontroller. So what that looks like graphically is, instead of mirroring our traffic from port 2 to our mirror port, we're mirroring it to the internal CPU port. And again, the CPU is making some decision on whether or not the packet should be seen. And if the packet should be seen, it's replaying it. So there's actually not a whole lot of code you need to pull off this attack. So 6net, the vendor in this case, was kind enough to include libpcap on their switch already. So all we had to do is grab the libpcap header files, toss them into our cross-compile environment, and then write code that uses the MDIO read, MDIO write, and fires up its own little pcap sniffer. It turns out a fully linked fake mirror binary here that does this whole attack is under 12 kilobytes in size. The flash file system on this is, I remember it's 128 megabit flash chip. I want to say there are like 3, maybe 4 megabytes free of flash space. So there's plenty more room to do other weird stuff and add your own utilities to this. So there's two problems with this attack technique. The first is that the real host or the real target will see duplicate packets. It's not really a big deal. Most hosts, if they see a duplicate transmit, they don't really care. The other problem is latency. And this is a weird problem that it isn't easy to solve, but also it seems like it's hard for normal intrusion detection systems to detect the extra latency that's introduced. So normally there's about 1.2 milliseconds of round trip time for typical low traffic, like 5 milliseconds. So somebody might notice that, but they probably won't. Another problem is that if somebody happens to log into the switch's admin interface while we're doing this, the gig could be up. It depends on the specific situation and how the original port mirroring was working. It can get a little bit dicey and something that we'd have to think about down the road. I'm not going to release the levered attack code publicly, but I did put those header files again on GitHub to give you at least the tools to think about developing this on your own. But it's pretty reliable IDS invasion or evasion. And one of the neat things is that the GUI is all file space. In other words, if you log into the switch admin interface and reconfigure the switch, it looks only to files. It doesn't actually pull the switch fabric to see what the configuration of the switch fabric is. So by rooting the switch, you get stealth for free. And probably most switches work this way, although we've only looked at this one specifically. The next attack we'll look at, I call the client attack. So mirroring, all that mirror manipulation was really fun, but another question came up was, can we filter network traffic? And can we, manipulate network traffic? In other words, go into the application layer of a packet and modify it on a network switch. And we would do this without using, something stupid like ARP poisoning, where we kind of use the internal CPU to man in the middle, because, ARP poisoning is noisy and everybody has ARP poison detection enabled on their network at this point, right? Right. I've asked this question at conferences before and been like, show me your, give me a show of hands, and nobody raises their hand. But you can probably guess that the answer is yes, we can do this kind of filtering, because why would I be mentioning it in a talk slide if the answer weren't yes? There's a lot of ways to pull it off. Of course, the most generic is to mirror the two target ports. In other words, the host A and host B that you want to get between to the internal microcontroller. You can add VLAN tagging to make sure that those two ports are on separate VLANs so that they can't possibly communicate directly with each other except through the microcontroller inside of the network switch. So what we're going to do is use the mirror port and use the VLAN tagging to swap the internal microcontroller between the two VLANs during receipt and transmission of the packets. That way we can effectively man in the middle without doing anything that actually introduces traffic on the network. So the cool thing about industrial is that it's almost all poll response, so we can actually kind of preemptively switch VLANs with each request so that we're ready to transmit to the right port without having to issue another MDIO command, kind of in between our packet manipulation. It's already done for us. So graphically, this is what it looks like. We've assigned our two systems to two separate VLANs. The mirrored packet goes into the internal CPU. The internal CPU modifies the packet, switches itself over to VLAN 2, and then transmits the packet as it looked originally. All right. So, the step 4 here is, how do we profit, right? So consider that we can do this packet manipulation with DNS. Of course, we have IDS evasion. And consider also that this is an industrial network switch. In the industrial space, there's no TLS wrapping on protocols for the most part. I mean, it's starting to get there, but not usually. Most of these industrial protocols have no encryption. They have no data integrity mechanism. So you can modify traffic and do some pretty terrible things with typical industrial protocol. So who's vulnerable? Well, almost any network switch that doesn't do firmware signing is going to be vulnerable to this, and a lot that do have it. Because remember that when network appliance like this has signed firmware, most of the time they're only signing firmware updates, but they never actually verify the integrity of a firmware that's already running. So if you find an RCE or some kind of shell level vulnerability in a network switch, you can modify the currently running firmware and there's no like detection of that. And so this can really affect any network switch with a hidden CPU interface. And that to tell if you have this, I mean, you could look up data sheets, but basically if you plug the network switch in and you can access the switch via web or telnet or SSH, and it has SNMP and all that sort of stuff, then it has this hidden CPU interface inside. So really think of these layer 2 switches as routers for the purposes of data integrity. These switch rootkits probably already exist for popular switches, would be my guess. It's doubtful that a lot of end users patch these things, and it's really impossible to audit these network switches without destroying them, right? This particular network switch, I mean, it happens to have JTAG pins and an internal serial console labeled, but you'd have to go, soldering stuff or at least connecting stuff inside, and you might destroy the switch, or at least you wouldn't want to use the switch after you do that. Really, the only way to verify the integrity of this network switch is to modify the firmware to give yourself root access to it. And by doing that, you're actually destroying evidence, which kind of stinks. So always manage your network switches from a dedicated management LAN. You should be monitoring network traffic to these admin interfaces. Make sure that your network management LAN is connected up to an IDS itself and that you're preserving some PCAPs. And check out your network equipment. Check out to see if this Cisco Smart Install service is running on your Cisco switches, and make sure that your management interfaces aren't exposed on a network that you think that is untrusted. And that is the end. So I'll take some questions. I think we have like a minute or two, if anybody's got them. Otherwise, you can hit me up on the Twitters as Reverse ICS or Cyber Pacifists, and I'll be around on the Discord for a bit too.
Cool. That was awesome. Let's see. Do we have any questions from the Discord, from the Twitch chat?
I'm looking around here. Must see any questions, but seems pretty good.